the QR code on your phone. And just want to apologise for that.
Next we have Tolga Birdal from Imperial College London. Yeah. He'll be giving a talk about like SignAvatars or large scale 3D sign language holistic motion data set and benchmark. Let's give it a class.
Yep. Thank you. Yeah, so this is my, let's say, first ever talk in to a sign language community. So first, bear with me if I cannot get all the details right. Because we started doing this work primarily by our interest to understanding humans in general. Objects, humans, environments, and scenes, right, in 3D and in 4D. So particularly, if you see this, you probably know this. What this is telling me is that... Could
you wait until the video finishes and then...
Right, of course. Yeah. So you see that, the singer is jumping out of the hall and starting to dance with the person. So this is telling me so much more. It's telling me that sign language is not just a tool for communication, but is a display, is a bodily act, right? And we can understand a lot about humans if we understand sign language, and I believe vice versa, right? So it's not only about communication, but it's also about capture and understanding how we express ourselves in general, and as such it's a great source of data as well. So we decided to go into this direction a little bit, and we observed that in 2D things are kind of there, although I still believe there is a lot to grow, but it's still kind of there, right? But if you start to go to 3D, that was when we started, unfortunately, it was quite an empty area. Okay, and the methods that were designed to do sign language production and generation from different kinds of languages or different conditioning signals were not there. So in computer vision, when you face such a situation, the first thing to do is to go and collect this data yourself. We don't know how to collect sign language data, of course, but we were glad to see that there were so many videos and so many translations, sign language videos available, and datasets, right? This was remarkable, actually. But these datasets were not gathered under a common umbrella. So as such, they were small. Okay, so what we did was to go ahead, collect all these, and annotate them so that we could train our supervised machine learning models on them, maybe. Right, so we present this SignAvatars dataset, and it consists of 70K videos and more than 8 million frames of both isolated and co-articulated signs, and we annotate them with simplex and mono annotations. Right, and it contains multiple subsets with different kinds of annotations, essentially. Right? So how would you do this? Well, we design an annotation pipeline that takes all these images and produces all these signals that I have been talking about. And these data sets are the ones you probably know much better than I do, right? And we kind of use them as an initial source and then apply the annotation pipeline that I'm going to talk about on it, and we get multiple subsets that are word level sign language, and then different languages, Hamnosis level, and so on. And all together, we combine and cluster them into one repository of datasets. Right. to do that, the first thing is actually to take all those images and design some kind of an optimization pipeline, which only uses learning in the initial part where we would like to detect these features from the images and initialize. And afterwards, there is some kind of a biomechanically plausible optimization going on to annotate all of these. Okay, so it's essentially, you can think of it as a fitting pipeline. So fitting, we do 3D pose estimation and 2D pose estimation. We ask for a consistency, and we add the biomechanical losses on top. So it's a multi-objective optimization problem. So once you do this, you can see that you get good isolated signs, okay, which we release, because we can release them.
Sorry, can I just say, when you're showing videos, if you could pause from talking, so they don't
Right.
let them see it, then carry on talking.
Yeah, of course. Right. So here, you can see the co-articulated sign. So it's a more continuous of a motion. And these are the results that, these are comparisons basically of the same thing to the state of the art at that time. You could see that there's a lot of jitter and, some inconsistent reconstructions. And this is just the optimization pipeline. A lot of the details are visible. Also, the shape capture is a bit better when you run this joint optimization, I would say. Not only that, we could also do full body reconstruction, because we are using these simplex models that have this whole, if you can learn a prior over simplex models, or if you can optimize, then you could also recover some of the full body parts, and that we can test separately on different data sets. Okay, so once this data set is there, it is possible to go ahead and apply it to different applications. There are multiple applications that we can address, but we specifically choose the sign language production out of these. And to do this, we have a bit of a huge pipeline. So this is the first model, so the initial model that we provide or present. So there are essentially two branches of this. One takes the language embedding and has this VQVAE, so vector quantized variation autoencoder type of an.
Sorry, you have to say that.
Right. Right. So it is an autoencoder with discrete codes. And then this reconstructs the language feature. And we have the holistic motion as input to the lower branch. And we have the decoded result. And that is a VQVAE, VQVAE on its own. Okay. So we have the appropriate corresponding loss functions in order to train this model. So these are the results I'm going to present. So this is a generation. What I just presented is a generative model. So on the right, we provide a reference. This is not exactly the same, and it should not be exactly the same. And here, the prompt is given in Hamnosis. That is one capability that we have. And we could also have English or different languages, German, and so forth. And there are two sources of errors here. First comes, of course, from our model, that it is not perfect. But the second one comes from trying to animate this character. So usually, the pure output of the of our neural network is a bit better than this. Okay, but I think still being able to do this transfer in 3D, it was quite new when we did it, and I'm sure now it is not. Another example. And maybe in German. Again, they will not match. They will resemble one another because we sample from the model. Okay, so that's all. That's what I wanted to present. And moving forward, we really want to seek a joint understanding of these things. You know, our models helping the sign language world, and the sign language world helping to build better models for general understanding of humans. So that's how I see it. And we do have a line of works for this. Right. So I should stop. Thank you for listening. I have a group at Imperial College. These are the people that I should give credit to. So thank you.
Thank you for the presentation. Due to the
And if we have time for questions, I'm really sorry. But
sorry.
Are you around this afternoon?
You can.
Okay, so people can come find you in the next break.
They can.
Okay.